Passing a 10,000-line codebase to a frontier AI model in a single prompt fails over 95% of the time. Welcome to the freshers. Today, we're learning about LoopEngineering. Raw foundation models score under 2% on real software bug resolution benchmarks like SWE Bench. Yet placing a smaller model inside an execution loop jumps task completion to 72%. PromptEngineering optimizes a single static text response, but it leaves the model completely blind to runtime errors. LoopEngineering builds an active workspace around the model to inspect, run, and self-correct work continuously. Think of a bare garage workbench holding only a locked instruction envelope. Without tools or engine access, even a master mechanic cannot fix a broken car from a paper note. That paper note is why static prompt engineering breaks on complex software tasks. Handing a single prompt to a language model is like slipping a sticky note under a locked garage door. If the mechanic's initial diagnosis fails, execution freezes instantly because single-turn prompts carry zero error visibility. An execution loop unlocks that door by building persistent agent state across iterative turns. The loop maintains a state buffer, recording historical tool actions, environment variables, and Python stack traces in memory. How can an AI model that guesses wrong on turn 1 fix its mistake by turn 3 without human help? Static prompts lock models out of runtime feedback, while persistent state gives models the memory needed to adjust execution tactics on future turns. Static prompts leave the AI blind to tools, but mounting a tool rack lets it reason and execute actions. We attach a wall-mounted tool rack to our workbench, loaded with shell terminal tools and repo search scripts. Before pulling a wrench, a mechanic checks the engine schematic. The React pattern forces the language model into an explicit think phase before touching any tool. The model writes its step-by-step reasoning trace into an explicit text thought block. Once the reasoning completes, the act phase dispatches a structured API command to the system environment. For example, the agent runs a bash search to locate the buggy file in the repository. This prevents impulsive mistakes by anchoring every tool call in deliberate logical planning. Running a terminal search command is useless if the system cannot inspect return results. We clip a metal diagnostic clipboard directly onto the workbench to capture feedback during the observe phase. Standard std streams, istd crash logs, and API JSON payloads write directly to our clipboard context. In the decide phase, the model evaluates this feedback against completion criteria to determine whether to stop or trigger another cycle. Here is the shocking truth. A compact 8 billion parameter model wrapped in this 4-phase loop routinely outperforms a 1 trillion parameter model stuck in a single prompt. Terminal tracebacks provide deterministic ground truth, allowing small models to make accurate system decisions without human guidance. Capturing live execution data transforms blind model guessing into precise software debugging. Having clipboard notes is only half the battle. The engine must automatically turn test failures into corrective code edits. We place our bug example on the workbench and turn the ignition key to run pested and unit tests. The engine sputters as unit test 14 crashes, flashing a red warning light on our bench. A raw Python KR stack trace on line 42 clips directly onto our diagnostic board. In a verification loop, this failure output becomes fresh input for the subsequent think phase. The model analyzes the trace, patches auth.py using file edit tools, and turns the key once more. The red warning light vanishes, replaced by a solid green pass signal across all tests. Self-correction repairs broken software without human intervention. Every test execution and tool output appends new text to the model memory buffer. After 15 iterative turns, your workbench is buried under hundreds of pages of terminal logs. This context window bloat inflates API token costs and triggers model attention degradation, where LLMs miss crucial instructions. We grab a shop wiping towel to perform context window management using state summarization. The towel sweeps away raw stack traces, replacing them with a concise 3-bullet state summary card on the bench. Pruning historical clutter keeps the active context window short, cheap, and focused on target files. Managing context window history prevents attention loss and keeps long-running agent state performing reliably. Without active pruning, context windows saturate and hallucination rates surge during multi-turn execution. A clean workspace prevents memory crashes, but protecting cloud budgets requires hard physical safety limits on execution depth. Without guardrails, an agent trapped in an infinite retry loop can execute identical broken commands repeatedly. That runaway loop can burn through hundreds of dollars in cloud API charges in under 5 minutes. We mount a heavy red safety circuit breaker directly onto the garage wall beside our workbench. The circuit breaker enforces recursion limits, capping work at 15 total tool iterations. If the agent exceeds this step threshold or breaches a $2 cost cap, power trips instantly. Halting execution protects cloud servers and stops unexpected financial losses before they occur. Hard safety guardrails transform unpredictable autonomous scripts into reliable enterprise software tools. Combining tool racks, clipboards, wiping towels, and circuit breakers builds a complete execution harness. This integrated stateful architecture powers modern production AI systems like Claude Code and Devin. Rather than relying on static prompts, multi-agent orchestrators like LangGraph pass state across specialized loops. A planner agent generates execution graphs, a coder agent writes patches, and a reviewer agent executes automated tests in sandboxed Docker containers. Retesting code automatically in verification loops elevates SWE bench bug resolution scores from 2 to 72%. Harness design is the single largest lever for unlocking real capability in modern artificial intelligence. That is everything you need to know about LoopEngineering today. Like and subscribe to The Freshers, and comment below what you want to learn next.